All right, let's get right into it. We're going to pull back the curtain on a math operation you've known your whole life, multiplication. And it turns out it's been hiding this incredible geometric secret. Seriously, it's a twist that's going to change how you see things.
You know, when you first learn about multiplication, it's all about scaling, right? 3 times 4 is 12. Things get bigger. Simple. But what if I told you that's not the whole story? What if multiplication could also mean rotation, like literally spinning a number around? That's the puzzle we're going to piece together.
So the setting for all this magic is what we call the complex plane. Now at first glance, it just looks like your typical XY graph. But here the horizontal line is the real axis and the vertical line is the imaginary axis. And every single point you can imagine on this surface, yeah, that's a complex number.
Okay, check this out. We start with the number 1, just sitting there on the real axis. Now let's multiply it by I. Bam! It hops 90 degrees straight up to the imaginary axis. Let's do it again. Multiply by I, and it swings another 90 degrees over to -1. And again, down to -I. One more time, and we are right back home at 1. How cool is that? Each and every multiplication is a perfect 90-degree turn. Wild.
So this is the big question, right? It almost feels like a magic trick. How on earth can multiplying by a number cause a perfect rotation? It just doesn't seem to make sense. Well, to figure it out, we've got to learn the rules of the game.
All right, so to crack this mystery, let's meet the main characters and lay down the ground rules. First up, the star of the show, this little letter I, the imaginary unit. Now you probably remember being told in math class, you can't take the square root of a negative number. Well, what if we just did? That's the whole idea here. We just define I to be the square root of -1. That's it. That one little rule, that I squared equals -1, is the key that unlocks this entire world. And when you take a regular old real number, let's call it A, and you mix it with an imaginary number, BI, boom, you get a complex number. Think of that A plus BI format as the unique address for every single point on that plane we were just looking at. Okay, so how do you actually multiply these things? Well, there's the standard textbook way, the algebraic way. And look, it works. It gets you the right answer. But it's also the reason the secret of rotation stays hidden. It's like our obvious suspect, but it's not giving us the whole story. You might remember this from algebra class. It's the FOIL method. First, outer, inner, last. It's just a handy little checklist for making sure you multiply all the parts. Nothing too fancy. Let's just run through a quick example. So we've got 3 plus 2i times 1 plus 7i. We just follow the steps. First gives us 3, outer is 21i, inner is 2i, and last is 14i squared. And remember, that I squared is our secret weapon. It's just -1. So the whole thing crunches down to a new complex number, -11 plus 23i. Done. And hey, it works. We get a correct answer. But do you feel like you understand rotation any better? Me neither. It's just a bunch of symbol pushing. It's a machine that spits out an answer. It gives us the what, but it tells us absolutely nothing about the why. So, to get to that why, we need to throw out the old playbook and look at these numbers in a totally new way. We need a different perspective. And it's this new perspective that holds the key. See, up until now, we've been thinking in what's called rectangular form. It's like giving directions in a city. Go A blocks east, then B blocks north. But there's a totally different way to give directions, polar form. Instead of blocks, you just say, point in that direction and go this far. So you describe the exact same spot using its distance from the center, which we call r, and its angle, which we call theta. This visual makes it super clear. That distance r is just the length of the line from the center out to our number. Its fancy name is the modulus. And theta is just the angle of that line. Its fancy name is the argument. Same location, two totally different ways to talk about it. Okay, now let's retry that multiplication idea, but this time let's use our new polar vision. We're multiplying 1 plus I times 3 plus I. Now the old way gives us 2 plus 4i. Fine, but let's look at the polar versions. Look at the distances. We have root 2 and root 10, and the result is root 20. Now look at the angles. We have 0.785 and 0.322, and they result in 1.107. Wait a minute, do you see the pattern? Something very, very interesting is happening here. This is it. This is the aha moment. The secret is about to come out. That little pattern you're probably seeing right now, that's the whole shebang. That's the key that unlocks everything. And the rule is just shockingly simple.
When you multiply two complex numbers in their polar form, you just multiply their distances together, and then you just add their angles. That's it. Let's check our example. What's the square root of 2 times the square root of 10? It's the square root of 20. What's 0.785 plus 0.322? It's 1.107. It works perfectly.
So here's the big takeaway. That whole algebraic FOIL method, it was just hiding this beautiful, simple geometric action. Multiplication of complex numbers isn't just a calculation, it's an instruction. It's a command. Scale by this much and rotate by this much.
And this takes us all the way back to the beginning. Why does multiplying by I cause rotation? Well, think about I in polar form. Its distance from the center is exactly 1, and its angle is exactly 90 degrees. So, when you multiply something by I, you multiply its length by 1, which does nothing. But you add 90 degrees to its angle. You get a pure, perfect rotation. And just like that, the mystery's solved.
But this is so much more than just a neat party trick. This idea that multiplication is rotation is an incredibly powerful tool that shows up in some really surprising places.
In fact, this whole principle gets wrapped up in something called de Moivre's formula. Now, it looks a little intimidating, but the idea behind it is brilliant. Let's say you want to raise a complex number to the 10th power. Instead of doing a ridiculously long multiplication problem, you just take its distance to the 10th power and multiply its angle by 10. It turns a nightmare calculation into something you can almost do in your head.
And this isn't just for math class. This connection between multiplying and rotating is absolutely fundamental to so many things. We're talking electrical engineering, signal processing, like the stuff that makes your phone and Wi-Fi work. It's even crucial in physics for describing the super weird world of quantum mechanics. Heck, even when you see something rotate in a video game or a CGI movie, the math behind it is using these very ideas.
So it really leaves you with a final, kind of cool thought, doesn't it? We took something we all thought we knew, simple multiplication, and we found this entire hidden world of geometry and rotation inside of it. It just makes you wonder, what other secrets are hiding in the math we use every day, just waiting for us to look at them from a new point of view?